Hello friends, I am Dr. Sudhan Sharma from School of Computers and Information Sciences, Indira Gandhi National Open University. In our previous sessions, we discussed about vectors wherein we understood about what are scalar quantities, what are vector quantities. We also understood about the direction ratios, direction cosines, explored the concept of dot product and vector products, cross product rather, and we understood about scalar triple product and vector triple product. We solved ample number of numericals and understood that the concepts of one unit are very much applicable into the other unit. In this unit also, we are going to discuss how the understanding of the vectors is applicable into the understanding of three-dimensional geometry. This is the third unit in block number 4, and wherein the concepts of three-dimensional geometry will be delivered, and you are going to understand what is a line segment and what are different equations of the line, and we are going to explore the different concepts for the three-dimensional geometry. So the objectives of today's session are in fact that in this session you are going to understand about how to determine the distance between the 2 points, and we are also going to understand the concept of direction cosines and direction ratios, which we already explored in vectors, and how to apply them in three-dimensional geometry when we are going to learn about the equations of the lines passing through 2 points. So this is I think self-explanatory diagram, and we explored this diagram m number of times. Say point P, X, Y, Z. This diagram is actually to let you understand what is a three-dimensional space. We are having a two-dimensional content, likewise X and Y is there. Then point P is represented by the component x1, y1. If O is the origin and OP is the vector, whose say R, so R vector is vector OP in two-dimensional space can always be represented with xi plus yj. But if the case is like three-dimensional as it is shown over here, then the vector OP will be given by xi plus yj plus zk. So because we are here to understand the concept of three-dimensional geometry, so that's why understanding of three-dimensional space is there. We are having, say, in general, the space dimensions are 3 dimensions, and the 4th dimension is your time. And that's why we are not going into the concepts that how what is the Hilbert space and how n-dimensional spaces are taken care of. We are restricting our discussion to 3-dimensional spaces only, wherein the triplet x, y, z is actually used to locate the point P, and in the coordinates, Cartesian coordinate system, we are going to represent in the terms of x, y, and z. We learned in the terms of vectors that the component representation of the point can always be in the terms of xi plus yj plus zk. We are going to extend the understanding of such concepts in this session. Now, the important concept, the geometry begins with the concepts of the points and the lines. So, if we are given 2 points, then the line segment connects the 2 points, and say point O is there and point P is there, then the distance between the 2 points will be given by OP vector. Now, say it is vector R, then you can always say that if O is the origin 0, 0, 0 and P is the point x, y, z, then OP vector is always given by R vector, and which is nothing but xi plus yj plus zk, which is given over here. And we also learned that the magnitude of vector OP will be given by the magnitude of vector this, and you can determine the magnitude by applying this formula. We already learned this formula in our earlier sessions when vectors were covered. In this session, we are going to revise some of the concepts which we had explored when we were discussing about the concept of the vectors. Because they are very much required, you need to refresh these concepts, because these concepts are required to be applied in the case of the understanding for the three-dimensional geometry. Likewise, over here you can refer to the figure. Say this is a figure wherein there are 2 points, point P and point Q. Say R2 is the vector which is pointing to point Q from origin, and R1 is the vector which is pointing point P from the origin. Then the distance between the 2 points, that is PQ, vector PQ will be given by the difference between vector OQ and vector OP. Vector OQ is nothing but vector R2, and vector OP is nothing but vector R1. And we all know that if x2, y2, z2 are the components or the coordinates of point Q, and x1, y1, z1 are the coordinates of point P, then R2 minus R1 will be equal to the component wise difference of the two vectors, that is x2i plus y2j plus z2k minus x1i plus y1j plus z1k. And subtracting the values I component from I component, j component from j component, and k component from k component, you will get this expression, that is x2 minus x1i plus y2 minus y1j plus z2 minus z1k. So R2 minus R1 is actually this vector. So in order to have more clarity, you can just look at the figure. You can see that R1 is the vector which is pointing from 0 to P, and QP is the vector which is pointing from vector point P to point Q. Then the resulting vector is R2. Applying the triangle law of addition of vector, you can always say that R2 is equal to R1 plus PQ vector. So R2 vector is equal to R1 vector plus PQ vector. So PQ vector, by rearranging, you can say is R2 vector minus R1 vector. So which is very much true over here, that is PQ vector is equal to R2 vector minus R1 vector. We simply applied the understanding of the triangle law of addition of vector, and we found that R2 minus R1 is the result, is the vector. You can determine R2 minus R1 by using this expression, by determining the vector PQ. We also explored the concept of the internal section and external section when we were discussing about the vectors, and this understanding is required to understand the concept of the distance between the 2 points. And wherein if we are having 2 points, say point A and point B, wherein x1, y1 is the coordinate of point A, and x2, y2 are the coordinates of point B, and there is some point in between, say point C, whose coordinates are x and y, such that this point divides by the line segment AB into the ratio m is to n. Then you can find the coordinates of this point by using the formula x is equal to m times of x2 plus n times of x1 upon m plus n. That means this is to be multiplied by this component of x, this is to be multiplied by this component of x upon m plus n. Similarly, y component of point C can be found by m times of y2 plus n times of y1 upon m plus n. So that means if there is an internal division, then we had already explored in the vectors, and we discussed that this thing in very detail, that if R1 and R2, say you can say that if we are having in the vector representation, say we are having this, and this is say point Q or point P, whatever you want to say this is point Q, and this is point P, this is point P, and this is point say something R say, and point P has got the coordinate x1, y1, z1, or x1, y1 simply, and point Q is having the point x2, y2, and point R is having coordinates x and y, and such that R divides in the ratio m is to n. This is the representation of the same section formula in the terms of the coordinates x and y. Then you will get the answer that R1, that vector R, it should be R, it should be R, not R1, m times of R2 plus n times of R1 upon m plus n, where R is the vector representing for point R. So we learned that if it is a 3-dimensional space, then internal section formula follows this, that is mx2 plus nx1 upon m plus n, m by 2 plus n by 1 upon m plus n, mz2 plus nz1 upon m plus n. Now, if point C, which is shown over here in this figure, bisects, that is, it is not dividing in unequal ratios, m is to n, it is just dividing in the format that m is equal to n, m is equal to n is equal to 1, then in that case, this corollary is followed, and we also discussed this corollary, that then the resulting vector R will be nothing but the midpoint of the two vectors A and B, and it is given by A plus B by 2. So in that case, when m is equal to n is equal to 1, then the coordinates x and y can be determined by x1 plus x2 by 2, y1 plus y2 by 2, and z1 plus z2 by 2. So this is how you can determine the distance between the 2 points. Also, you can say that if 2 points are given to you, say point A is there, point B is there. Likewise over here, or for the sake of simplicity, you can say that point P and Q are given to you. Point P and Q are given to you. Point P is having the coordinate, say in this case, as 1, minus 1 and 0, and point Q is having the coordinate 2, 3 and minus 1. Then vector PQ will represent OQ vector minus OP vector, and this is the distance in between the two. So that means the magnitude of of PQ vector will be given by x2 minus x1 I square, x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. So over here x1, y1 and z1 are given as 1, minus 1 and 0. x2, y2 and z2 are given over here as 2, 3 and minus 1. So x2 minus x1, y2 minus y1, z2 minus z1. z1 is this. So you got the answer. 2 minus 1 is 1, 2 minus 1 square is 1, 3 plus 1 square, 4 square, that is 16, minus 1 square is 1. So overall you got square root of 18, and that turns out to be 3 root 2. So the distance in between the two will turn out to be 3 root 2. So I hope you understood that how to find the distance between the 2 points. The distance between the 2 points is very much given by this expression, that is square root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. We also learned that how to determine the coordinates of a point which is bisecting the distance between the 2 points in some ratio m is to n, and we learned by solving one numerical also. Now it's time to understand or revise the concept of direction cosines and direction ratios. We learned in our earlier session that if we are into a 3-dimensional space, say x, y and z, and there is some point where vector r, which is from point 0 to point P, having coordinates x, y, z, or x1, y1, z1, subtending angle alpha, beta, and gamma with the positive axis of x, y, and z axis, then cos of alpha will be represented by L, that is direction cosine, cos beta is equal to m, and cos of gamma is equal to n. So cos alpha, beta, cos alpha, cos beta, cos gamma are the direction cosines, and they are represented by L, m, and n. And we also proved also in our earlier session the important property that L square plus m square plus n square is equal to 1. Now we also explored that if A, B, and C are the direction ratios, L, M, N are the direction cosines, and A, B, C are the direction ratios, then you can always write direction cosine L is equal to direction ratio by the magnitude of the vector r. The magnitude of vector r with direction ratio A, B, C can always be written as square root of A square plus B square plus C square. So that means L is equal to A by R, M is equal to B by magnitude of R, and N is equal to C by magnitude of R. So that's why you can always say that L is equal to A upon square root of A square plus B square plus C square, M is equal to B upon square root of A square plus B square plus C square, and N is equal to C upon square root of A square plus B square plus C square, where A, B, C are the direction ratios and L, M, N are the direction cosines. And this represents the connection in between direction ratios and direction cosines. And there is one more important relation, that A upon L, that is ratio of direction ratio and direction cosine, this all are equal. Now say we are given a vector V, which is equal to AI plus BJ plus CK, and where A, B, C are the direction ratios, then its direction cosines are, we already learned that it is equal to A upon square root of A square plus B square plus C square. And similarly B is equal to this upon this, A square plus B square plus C square, and similarly for N. We also learned that L square plus M square plus N square is equal to 1, that is cos square alpha plus cos square beta plus cos square gamma is equal to 1. And we learned that cos alpha, because we know that cosine cos theta is equal to base upon hypotenuse. So if we are having, say, in a two-dimensional system, theta is the angle, then projection will be say this is r, so this will be on r cos theta. So this projection will be equal to r cos theta. R cos theta is nothing but the projection on x axis. That means you can say that x is equal to r cos theta. That means cos theta is equal to x by r, and the angle which is made by x axis is nothing but alpha. So you can always say that cos alpha is equal to x by r. So cos alpha is x by r, cos beta is y by r, and cos gamma is z by r. So where you can say that x, y, z are the direction ratios. Likewise over here we had said that cos alpha you can say is if vector r is ai plus bj plus ck, ai plus bj plus ck, then it is always true that L is equal to a upon magnitude of r, that is a square root of a square plus b square plus c square. So I hope you are able to recall what we had discussed in the session for vectors. Now one more important concept which we had already discussed, that say A and B are the 2 points. Looking into this figure, a point A is there whose coordinates are say x1, y1, and point B is there whose coordinates are say x2, y2. Then the distance between the two will be given by vector AB, which is equal to R2 minus R1, where R1 and R2 are the position vectors for point A and point B, and you can always say that R1 is equal to x1i plus y1j, and R2 is equal to x2i plus y2j. Therefore, the position vector from point A to point B giving the distance between the 2 points can always be written as x2 minus x1i, y2 minus y1j, z2 minus z1k. And therefore, you can always say that the direction cosines can be represented for the vector AB as x2 minus x1 upon magnitude of r. What is magnitude of r? That is magnitude of AB. So, x2 minus x1 upon magnitude of r is equal to direction cosine L. Similarly, m is equal to y2 minus y1 upon magnitude of r, and similarly n is equal to z2 minus z1 upon magnitude of r, where r is equal to r2 minus r1. This is equal to vector r. So, in the terms of direction cosines, you can say that if A and B are the 2 points such that A is x1, y1, z1 and B is x2, y2, z2, then the direction cosines are given by the formulas L is equal to x2 minus x1 upon magnitude of AB, m is equal to y2 minus y1 upon magnitude of AB, and and n is equal to z2 minus z1 upon magnitude of AB, where AB is the distance in between the 2 points A and B. Now, let us solve one numerical. Over here, we are required to find the direction cosines of the line which makes equal angle with axis. So, that means equal angles are there. So, that means all angles made by say this line alpha, beta and gamma all are same. So, since cos alpha is equal to cos beta is equal to cos gamma, and you say that this is L, this is M and this is N, and since all are equal, you can always write them equal to all as L. So, by using L is equal to M is equal to N in the identity L square plus M square plus N square is equal to 1, you can always write, because L is equal to M is equal to N, you can always write L square plus L square plus L square is equal to 1, that is 3L square is equal to 1. That means L is equal to 1 by 3 square root. So, that means you are going to have L is equal to plus minus 1 by square root of 3. Hence, you are, because L is equal to M is equal to N, so L is equal to M is equal to N is equal to 1 by plus minus 1 by square root of 3. Now, let me solve one more example for you. Find the direction cosines of the line passing through 2 points this and this. So, point A and point B are given to you, that is 1, 2, 3 is a point A and minus 1, 1 and 0 is point B. So, 2 points are given to us and we are supposed to find the direction cosines, and we know that the direction cosines in such case are given by L is equal to x2 minus x1 upon magnitude of AB. So, what is magnitude of AB? The magnitude of AB should be equal to square root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. So, what is x1? In the given expression, the points, this is point x1, this is y1 and this is z1. Similarly, this is x2, this is y2 and this is z2. So, this is x2 minus x1. So, x2 minus x1, this is y2 minus y1, wherein y1 is this. This is z2 minus z1, minus of z1. So, the z1 is 3. So, solving this expression, you got that magnitude of AB turns out to be square root of 14. Now, substituting the values in these equations, you will always get x2 minus x1, that is minus 1 minus 1 that upon square root of 14, that is equal to minus 2 upon square root of 14. Similarly, m is equal to minus 1 upon square root of 14, and similarly n is equal to minus 3 upon square root of 14. So, we found the direction cosines of a line passing through 2 points A and B. And this was all about the revision of the concepts we learned in the vectors, and we are going to apply these concepts when we are going to extend our discussion for other concepts in 3-dimensional geometry, that is unit number 3 of our block 4 in our subsequent session. So, this was about to revise and try to practicize the problems, and we are going to expand our discussion for 3-dimensional geometry in our subsequent session. Thank you.